Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, my name is Teacher Jean-Marie, and welcome to this TV learning program. I will be teaching you physics into this session. Thank you. Now, student, you have always to remember to take your notebook, physics notebook, for writing some explanations, the exercise notebook and the calculator to perform and work on the activities that you are given. Let's now begin. Our lesson today is about revision on sound wave. This is unit 1 that you saw in senior 6. It was a unit that was given to you at the very beginning of this term. So before we start, what do you remember? What do you know about wave? Okay? Yes, student. As you know, wave is a disturbance of the medium that transfers energy from one place to another. And this wave transfers energy that is amplitude. And it transfers also the information. This is the frequency. And then it is transferred from one place to another. About amplitude and frequency, you remember that. Okay. Now, student, in senior 5, you have studied again what you know as the properties of waves. What are these properties? Okay? Yeah. Properties of waves are reflection, refraction, diffraction, and interference. Yeah, you are great. And let's now talk about the examples of waves that you may know. What are they? Okay. Yes, student. These examples, they are, of course, given according to the category in which these waves are classified in, to whether they are mechanical waves or electromagnetic waves. Of course, the example that you can give, a mechanical wave is a sound wave. That is a good example. And the example that you can give for electromagnetic wave is light. Look around you, and then you find light. That light is an example of electromagnetic wave. Now, as you have said, we are studying sound waves. This is unit 1, as you have introduced it. Okay, students. Now, what is a sound wave? This is the definition. What is a sound wave? Yeah, that's great. Sound wave is a pressure that is caused by the vibration of the medium. And as we have said, it transfers energy from one place to another. That's good. And student, can you now ask yourself why, if there is an exploded planet, we cannot hear the sound, yet it is a very huge sound? That's true. The reason why we cannot hear the sound from that planet, from that exploded planet, is because there is no medium between our Earth planet and that exploded one. That's true. Now let's talk about the properties of sound. What are they? Properties of sound waves. So we have said that sound wave can reflect. That is reflection. It can also reflect. This is reflection. Can also deflect. This is deflection. And then interference. Interference of sound wave. Now, as you know, the reflection of sound is when, of course, there is a reflected back of the sound when it reaches the obstacle. And what do you think by the reflection? That's true. The reflection is when it enters, it is transmitted into another medium. Of course, this is when sound is from one medium into another medium. And then we have deflection. This is when it moves around the obstacle. When it is around that obstacle, then we talk about deflection of sound wave. Interference, and this is what we can now see into the formation of the standing waves into the pipes. Now, students, I want you to talk about how do you think sound wave is produced? So sound wave is produced when you vibrate the material. When there is a vibration of the material, and that time there is the sound wave. And I'm going now to give you the example because, as you remember, the definition that I have said, do you remember that? I've said that this is the pressure. Pressure that is caused by the vibration of the medium. Now I have this material here. Since there is air inside here, and then whenever I vibrate, there is a sound. Do you hear that? Let's start that again. Do you hear that? Again? Again? For this one. Do you hear that? Now you have said that sound wave is produced when there is a vibration of this material, and it is vibrating the air. That is the medium. So before we talk about the types of sound waves, let's now recall again to what you remember as how fast the sound is maybe into solid, gas, and liquids, fluids. Student, can you talk about how you think sound is moving into solid compared to how it is moving into gas. That's nice. Sound waves moves faster into solid, but into gas, it has a speed, because that speed is a value. It is around 330 meters per second. Now, let's talk about the types of sound waves, as I have said. How many types that you know? Yes, there are three. These three types of sound waves are, one is what is classified into the range that is enabling you to detect me. And this is what we call audible range. That is one. And this one, then we have the types of sound. So we have one is audible range. And this is into 20 hertz to 20,000 hertz. You see, it is a very big range. And then we have another type. This is number 2. It is what we call what is this? The word here, do you see it? This is ultrasonic sound wave. You get that one. And then number 3, it is the infrasonic sound wave. That's one. Now, what do we define as the ultrasonic sound wave? These are the sound waves that have, these ones, they have the frequencies that is above the audible range. It means that this one, they have frequency which is greater than 20 kilohertz. If I say 20 kilohertz, you understand that this is 20,000 kilohertz, right? Okay, students. Now, number 3 here, this is what we have said as the infrasonic sound waves, and these are the sound waves that have a frequency that is below the audible range. In other words, the frequency here, the frequency is less than 20 hertz. Do you see that? And then we have the infrasonic sound waves. Now, let's talk about the standing waves of sound into the pipes. We have the different types. We have 2 types of pipes into which we have the formation of sound wave. And as you remember, this is one of the devices that can help us to just to produce the sound. We have one here, and this is the open pipe. In the open pipe, as you see, we have the formation of this antinode. We have formation of node, and this is for the first mode, and the second one, and the third one. Now, here we have the length of the pipe, and as you see, it is open at both ends. Then you see the length here. You see the length? The length is equal to the half of the wavelength. That's true. And then number 2 here, This is where the length is equal to wavelength. And then number 3, we have L, that is the length, which is equal to 3/2 wavelength. That is lambda. And let's come back to the frequency. The frequency that we are saying here, the frequency that I'm saying there is the one that we find from the speed times the wavelength of the wave. Now, if we use this formula, and then we find that every time we just use what we have now calculating there, it is the frequency. And then for that number 1, this one, for this number 1, for example, you find that we have F1, which is going out to be equal to the speed, but what we want is lambda. And that lambda is going out to be equal to, this is lambda here. You see, it is going out to be to 2L. Do you find that? Yes. And this is over 2L. That's why now, into this diagram, you have, this is V over 2L. And if you proceed, then you find that we have this frequency number 2, frequency number 3. Okay? In general, that is the formula. The general formula is going out to be that is Fn, which is equal to, do you see what is changing here? You have here, this is 1, and there is 2, because for number 1 here, you have V over 2L, and you have F2, which is equal to 2V over 2L, and then in number 3, you have a 3F, V over 2L, and then in the general, when you continue, you find that Fn will be equal to what? Yes, N V over 2L. And then you find that N here will always be equal to 1, 2, 3, and so on. And then we have this as the general formula, but when you have an open pipe, then let's see the closed pipe. For the closed pipe here, this closed pipe, we have, in a similar way, we have L, which is equal to lambda over 4. And this is the closed pipe at one end. And then we have the corresponding frequency as how we have determined it here, using this formula. Do you see that? Okay. So then, F3, it is also equal to 3, 4 over, this is the speed over 4L. And in general, we find that F equals to, this is for the open pipe, and then for the closed one, closed pipe, what do we have? Well, this F1 equals to what? Yes, that F1 equals to 4 to that V over 4L. And then we find this F3, which is equal to, this is 3V over 4L. And then we continue, but we find that if we say this is N, V over 4L, N here will always be a odd number. That is 1, 3, 5, 7, and so on. Now, before we have just the numerical examples on this formula, let's talk about the application of sound wave. What is the application of sound wave? Application of sound wave is when we have a Doppler effect. Can someone just tell me what is Doppler effect? Yes. Doppler effect, as you were saying, is an apparent change of frequency or wavelength, which is due to the relative motion of the observer or the source of sound. This is so we have one Doppler effect. So Doppler effect is the apparent change of frequency or wavelength due to the relative motion of observer or source of sound. This is the definition. And then give the general formula of that, Doppler effect. Do you know the general formula? That's great. A general formula that you think is correct. And this is given as FO, which is equal to the speed of sound in the air plus or minus the speed of observer over the speed of sound in the air minus plus here the speed of the source of sound times the frequency of the sound. And this is the formula. But you can know whether a car or a sound source is moving toward or away from you according to this sign. If the car is moving away from you, that is the source of sound, then you have the low frequency. You are detecting a low frequency. But when it is moving toward you, it is approaching you as the observer, the frequency is very high. That is what you detect. And then what is another application of that? Application of sound wave. That's true. It is applied into what we call echolocation. Echolocation, and this is the way some animals use to hunt the insect. Let's say bat. Bat will now use this frequency, that is the frequency, sonic frequency that they use to hunt the prey, to hunt the insect. And it is also used in medicine, like getting like now when they are going now to use it to analyze the development of a fetus. Now, let's have the exercises. These are the exercises that we are going now to do. But before that, you remember what I'm teaching you, students? Do you remember that? Oh, that's it, true. So you get that one. That is physics, but especially senior 6. And I know that you want now to have the exercises that we are going to use to apply the formula that we have used. And then here we have these examples. We have number 1. As you are now copying something here, a pipe is 2.46 meters long. Determine the frequency of the first 2 harmonics if the pipe is open at both ends. What are the 2 lowest possible frequencies if the pipe is closed at one end and open at the other? Number 2, if you hear the horn of the car whose frequency is 216 Hertz at a frequency of 225 Hertz, what is its velocity? Is it moving away or toward you? Let's now answer. So we have that is the open pipe. And remember what we have said as the open pipe. And the general one is this is the correction. Number 1, we have, this is Fn, which is equal to N V over 2L. And then the 2 harmonic frequencies. This is 1 is equal to, this is 1. Then the speed of sound is 343 over 2 times Z 2.46, and then the answer here will be in Hertz. Can you find the answer? Okay. Then frequency number 2 will be equal to 2 times 343 over 2 times 2.46 Hertz. And then you find the answer to that one by applying the calculators. Okay? Now let's see how you have to solve the question number 2. That number 2 is what applies the Doppler effect. Do you understand? So as we have said, this number 2, we can now say that, okay, first of all, there is a frequency of the source. This is equal to 2. Then this is equal to 216. And then the frequency of the observer, you are detecting 225 Hertz. And as what you see, the car is approaching you as the observer. And then you use this formula here. You have a V over V minus Vs. And then you have to multiply by Fs. When you substitute the data that we have, you find that we have 225, which is equal to 343 over 343 minus Z, V that we want to find, times 216. And then you solve this question, you find the answer. Okay, students? Can you go and send the feedback to your teacher? The teachers are the answers for all of the questions that you are asking yourself. And I hope you are following the instructions that are continue to be given to you during this period. And I hope to meet you again. Thank you. Bye-bye.